M1 and M2, and we can bring them together in a way that creates a new machine, a new Turing machine, M, that is a decider, right? It will accept all the strings in the language A, and it will reject all the strings not in the language A. We can construct this machine M from M1 and M2, and here's the description of M that makes it a decider of A, right? So as usual, here's your formal description of the algorithm, or the Turing machine, same thing. An algorithm is what a Turing machine does. Okay. So you begin with a description of the input tape to the Turing machine. So it's just some arbitrary, well, not arbitrary, some string that belongs to the language A. Yeah? So W is just any element of A, language A. Right. This machine M, it has as components two machines, M1 and M2. And M will run them both in parallel on this input string W. So effectively it's inputting W to both these machines, M1 and M2. Right? Now if M1 accepts, then M will accept. And if M2 accepts, M will reject. Can you does that sort of seem obvious to you, why you do that? Now, a bit of a comment now. Oh, look, by the way, you can see it's getting really dense here. You can appreciate why that happened. If I'd gone at my usual density, I would have had like 3 or 4 lines left over for a whole new board, and I didn't want to do that. I really wanted to finish and get to the punchline, give you my trumpet roll, and come to this amazing conclusion at the end of the board. So of necessity I had to bunch up a bit, so the density has increased quite a bit, so I hope you can follow this quite well still. Alright, so a bit of comment on what does it mean to have like two machines, two part Turing machines running in parallel. What does that mean? Well, so you have machine M, which has M1 and M2 as parts. So this machine M will have like 2 tapes, right? One tape will be for simulating M1, and the other tape will be for simulating M2. And then you can have a machine executes one step on machine 1, followed by M executing one step on machine M2, and it alternates. M1, M2, M1, M2, and so on. That's effectively what's meant by in parallel at the same time. So you've got these two machines going. Now you keep doing that. One alternate, M1, M2, M1, M2, step at a time, until one of them accepts, right? And then you make your decision. Either you accept or you reject. Right? Now look, any string whatever, it will either belong to that language A, and if it doesn't, well then it must belong to the complement by definition. Right? So any string, or every string, well any string belongs to either A or to the complement of A. Right? So for any string then, either M1 will accept or M2 will accept. Okay. So if M1 accepts, M will accept, and if M2 accepts, well, M will reject. So in other words, M is deciding; it always holds. Okay. So it's M then is a decider, right? So it accepts all. It'll accept all strings W that belong to the language, and it'll reject all strings W that don't belong to the language. In other words, belong to the complement of the language. Okay? So that means M decides the language A, and therefore A is decidable. So that's from right to left. That's the if Q then P half of the if and only if proof done. Now the other way, from left to right, P arrow Q, if P then Q, P, oops, this should be only if, P only if, P only if Q. In other words, P can only be true if Q is true. So if P is true, then Q has to be true. Right? So P arrow Q. In other words, from the left-hand side to the right-hand side. Now, what is the left-hand side? Language A is decidable. Okay? And from that, you have to deduce the right-hand side. In other words, the language A is Turing recognizable, and the complement of the language also Turing recognizable. That's what you have to prove. Let's see. Well, if a language A is decidable, well, then it's Turing recognizable. Remember that statement being made by Sipser quite a while back, and it didn't seem at all obvious to me at the time. Now it seems very obvious. Why? Because, well, consider the two definitions. Decidable, what does that mean? It means, here's the definition, that there's a Turing machine that accepts all strings belonging to the language and rejects all strings not belonging to the language. Okay? That's what a decider is. Now, a Turing, a recognizer, that's a Turing machine that accepts all strings belonging to the language, and that's it. There's nothing else. There's no more words in the definition, right? So can you see that a decider, as part of itself, is a recognizer, because a decider is a recognizer plus it has more can do more things than just recognize. It can also reject all the strings that are not in the language. Okay? So a decider also performs the task of being a recognizer. So any deciding Turing machine is also a recognizer. So we've got that part done immediately. Right. Let's see. Now, the complement of the language A is also decidable. And if it's decidable, well, then it's Turing recognizable. So how do you prove that it's decidable? Well, you could create. It's not discussed in the text. I'm just thinking in real time here. You could create a Turing machine, well, sort of like D. What D did to H, it just reversed. So you could create a Turing machine. So if A is decidable, A bar, the complement, is also decidable. How do you show that? Well, then you create this machine that outputs the opposite. So let's assume A is decidable. So it has a Turing machine, let's call it P. And let's create a second Turing machine, let's call it Q. And Q outputs the opposite of what P decides. So let's see. There's two machines, P and Q. So P will accept all strings of A and reject all strings not in A. And Q will do the opposite. It will reject all strings in A and accept all strings in that are not in A. So all strings that are not in A, by definition, that's the complement of A. Okay, and all strings that are not in A are in the complement of A, and they're accepted by Q. So Q decides the complement of A. Okay, therefore complement A is decidable because there is a Turing machine called Q that decides that language, the complement of A. Right? Okay, so if A bar is decidable, I've just shown it wasn't in the text. He just assumes it. Again, Sipser and his MIT students. We've just shown that A bar, the complement, is decidable. And just before, if it's decidable, then it's T recognizable. Okay. So we've shown that both A is Turing recognizable and the complement is Turing recognizable, and that's what mathematical statement Q. Oh, confusing, right? P and Q. Okay. All right. We're getting very close to the punchline and trumpet roll. So we now have a corollary. So 4.23, and here's a corollary is just usually a quickly derived, fairly easy theorem that comes from a previous theorem, usually much heavier and harder. So here's the theorem statement, or the corollary statement, same thing. Well, I mean, a corollary is a theorem. The complement of ATM is not Turing recognizable. So here is the language we are looking for. Okay, ta-da! Getting close, right? So it's not ATM, because we know that that's Turing recognizable, but the complement of ATM is